Welcome to the System on Chip Extension Technologies presentation. We are a team consisting of over 50 students involved in the disciplines of electrical engineering, computer engineering, and computer science, collaborating together to hone our skills while fabricating a microcontroller. The following slides will detail our subteams and what they've been working on this semester.
Radiation hardening, or RadHard, is a brand new subteam to SoCET this year, created by electrical engineering students. The subteam was formed to research techniques for protecting circuits from excessive radiation and then integrating them into a chip iteration. The main application areas for this are in areas where lots of radiation is expected to be found, such as in space, air travel, around nuclear power plants, or near X-rays and lasers. Since this was the team's first semester, their main goal for the semester was to gain enough background information in order to determine future projects that would be most fitting for them. The first of these projects is a simulation of the impact of radiation in Cadence Virtuoso using skill scripting. The scripting would be used to implement an algorithm which Virtuoso would use to put current sources into a schematic to simulate charge injections due to radiation. The second of these projects would be using an FPGA that's able to detect errors due to radiation effects and then reconfigure itself to account for these errors. The digital design subteam is a subteam comprised mostly of computer engineers, whose goal is to use System Verilog to model the functionality of the ASIC design. Their current work is mostly focused on extending the RISC-V instruction set architecture from RV32I, or the base 32-bit instruction set, to RV32IMFC. Each of these additional characters off of the RV32I corresponds to additional functionality. The M is for integer multiplication and division and adds 8 additional instructions to the instruction set. The F is for single precision floating point values and adds an additional 25 instructions. And the C is for compressed instructions and adds an additional 36 instructions. These compressed instructions have smaller size, which allows them to be used more quickly than the normal sized instructions. Other projects being worked on by the digital team include a software-controlled power management unit to disable unused peripherals, which would help with power consumption, multi-core with cache coherence and atomic extensions for atomic operations, integrating interrupt controllers, an I2C peripheral, and an SPI peripheral to allow for more communication with external devices, and adding periodic interrupts and pulse accumulation to the timer peripheral. The Universal Verification Methodology, or UVM subteam, is a subteam primarily composed of computer engineers whose focus is using UVM in order to write System Verilog test benches that can be used to test SoCET designs. UVM uses random test vectors in order to simulate the device under test, using a set of standardized components including a sequencer, driver, monitor, predictor, and scoreboard. The advantage of using UVM is that the standard components mean that they can more easily be reused, allowing test bench generation time to be shorter, and the creation of additional test benches to be easier. The UVM subteam this semester is focused on 3 major projects: the verification of the CLI-NT and PLIC interrupt controllers, as well as the I2C. The verification of the interrupt controllers is very important, as if they do not work properly, the processor would not be able to work at all.
The ongoing projects for the analog design team include an on-chip linear dropout voltage regulator, a rail-to-rail digital-to-analog converter, an analog-to-digital converter, and the ongoing design of an on-chip wireless radios components. The on-chip linear regulator enables a device to be compatible with 3.3 volt power supplies and ensures the voltage and power delivered to the chip is safely regulated. The purpose of the rail-to-rail digital-to-analog converter is to convert the digital on-chip signals into quantized analog lag signals to allow the SoC to generate close to sinusoidal wave functions. Moreover, wireless radio components are being designed to operate on the ISM radio band at 950 MHz, which is compatible for Zigbee communications. The future analog projects include working on the Intel 22FF FinFET technology node to improve upon the previous radio design to fabricate a full wireless transceiver and receiver capable of operating at millimeter wave frequencies. Additionally, 2 versions of ADC and DAC will be created, a high-speed, low-resolution, as well as the one that is low-speed and high-resolution.
The PCB team does the design and assembly of the board layout in order to create a testing and verification platform for SoCET's fabricated chips. The team uses an open-source PCB design suite called KiCad to develop the team's boards. The two most recent socket chips the subteam is assembling and designing PCBs for are the AFT-X04 and the AFT-X05. The assembly of the X04 system consists of 1.2 volt to 3.3 volt level shifters for interfacing with other components such as the USB UART integrated chip, which allows for interfacing with the desktop. The PCB also consists of a wall power supply that is delivered through a barrel connector and switching regulators. The ZIP socket will be used to mount the chip onto the board, and for testing purposes, buttons, switches, and LEDs will be connected to the GPIO pins, which are used in a boot-up self-test program. In addition, we are in the process of designing the layout for the X05 board, which will be a test board capable of application-based testing, such as number recognition and structural fault detection. The X05 will consist of a power supply, GPIO, a 2 MB external SRAM, and a current sensor to display the drawn current.
This summer, we have been very busy on the software team. We have been doing a lot with the Rust programming language. Rust is a very useful programming language, which has made it the most loved programming language since 2016 according to an annual Stack Overflow survey. Rust is syntactically similar to C++ and was designed to make safe programs. Rust has many advantages, with a clean, modern compiler and unique features like cargo packages and crates, but some of the biggest draws to the Rust programming language is that it guarantees memory-safe programs, which means no seg faults. Rust is also very capable with both low-level system programming and higher-level programming applications, which allows for one to use the same language across many projects. This summer on the software team, we have been focused on developing drivers in embedded Rust to operate the AFT-X06, and also developing sample applications in Rust to demonstrate our capabilities and also discover potential issues.
For the past few months, the Design Flow subteam has been focusing on the implementation of the open-sourced system-on-chip design tools that were part of the Skywater Process Design Kit. Our main goal was to successfully get our design ready for tape-out and admit it to the MPW2 eFabless run that had been sponsored by Google specifically for these tools. The submission having been on June 18th, we are happy to report that our submitted design, the AFT-X06 Caravelle, which utilizes the RISC-V core, was accepted and will be part of the designs that are fabricated as part of the MPW2 run. Since our project submission, though, we have also been working on a couple of projects in which we are currently leveraging the advanced design kits that we have been given access to, in addition with our existing IP, to create a design utilizing 5G technology for research purposes. During this time, we will also be making improvements to the IP while researching and developing means of preventing side channel attacks for other designs. Finally, as part of this process, we are also setting up a synopsis flow and learning the tools for future use which are listed below, so that development of future designs will have greater flexibility.
This team introduces students to the SoCET team through a series of tutorials to give them a wide range of skills in the physical and digital areas. They will get hands-on experience in chip design similar to industry level. Students will learn programs such as Cadence Virtuoso, KiCad, and System Verilog. Intro to SoCET will be an addition to a subteam to allow students to apply what they learn. The tutorials include Intro to Physical Design, Intro to Analog Design, Intro to Design Flow, Intro to Digital Design, and Intro to PCB. New tutorials such as Op-Amp Design Tutorial and UVMF tutorial are new this year. And in progress are a Magic tutorial along with an Open Lane tutorial.
Coming to the end of our presentation today, we would like to extend a warm thank you to those who are watching and hope that you enjoyed our presentation. In addition, we would also like to thank our sponsors and collaborators for allowing such updates and projects to occur. More specifically, thank you to those associated with VIP, the Vertically Integrated Projects, the Indiana Innovation Institute, the Naval Surface Warfare Center Crane, Scalable Asymmetric Lifecycle Engagement, SURF, and the Discovery Park Undergraduate Research Internship Program. We wish you all a good day, and goodbye.